I've started. I've started. Please just calm your. No talking. All right. Now, just a quick little recap. I omitted some writing, but I'm just going to quickly scribble it down over here as a revision. The other class, I didn't get to this in time. And when I changed the resolution, it screwed up the screen capture. So I just want to repeat what you've already written. We're going to say that the sum of all forces can produce F centripetal, which we know to be mv squared on r, which could also be m4 pi squared r on t squared, which can also be m4 pi squared r f squared. Please recall, this is in datasheet, as is v equals 2 pi r on t, as is a centripetal equals v squared on r. Those are the only three equations that you have. So just remember, all the other equations need to be derived from the other, v equals 2 pi r on t, and frequency being the inverse of the period. You already wrote this down, but I just want you to recall that this is not a real force. It can be produced, because it's the sum of all forces acting on an object, can be unbalanced. We call it the net force. It's Newton's second law. Sum of all forces equals ma. In this case, it's not translational acceleration, it's rotational or centripetal acceleration. It can be produced by any other force. So tension, friction, gravity, applied force, the normal force. Okay, those are real forces that act. Okay, centripetal, not real. There has to be something pushing or pulling or applying an actual force to produce that motion. Okay, now here's where I'm going to go into potato mode, because I want to look at our first example. Recall that it's sending too much information to the airtame, so I need to make it send less information by going into the potato matrix. Keep changes. Yes, no, I like my blurry apps. So, here's the video, gents. This video relates to the image of the CD. So can you have your booklets open to the page of your CD? I didn't mean to press full screen, but hey, let's do it. Actually, I just want to check that we're still going. We are still going. Okay, 18.7.
Sort of like 80,000 RPM, this one. So we'll be able to shatter the CD with this.
How small do you think the CD pieces will be?
I reckon there'll be dust.
Dust?
Dust. Yeah.
Dust?
There'll be dust. Just a little bit of dust. Yeah, we've hooked it up, got two washers here to secure the CD, and then bolted it in. Just going to spin it around.
So I'm excited because we're using a new Phantom today. This is the V2511, and it's the fastest camera we've ever used. A 720p will do 28,500 frames a second, and at its lowest resolution will do 1,000,000 frames a second.
So we've hooked up this Variac to the Dyson motor so that we can vary the speed and the power going to the motor and then dial it up until it breaks and shatters and see what RPM we get to.
So this is essentially what they are doing.
Dan?
I've paused it. Let's just go forward a bit. We'll put some sound on.
Fast enough to see what happens.
Oh, we missed it. Here we go.
Yeah. I thought it was going to go to the moon. It went higher than it did before. I went to like 100,000. Did it really? Oh.
Watching.
So as you can see from this, 2,500 frames a second isn't nearly fast enough to see what happened there. Let's look at what we got.
Right. You can see it warping. Look at that.
Whoa.
It's moving so much.
Oh my god.
Look at the shape of it. It's moving, like the whole thing. Whoa! Oh my god! Oh man, that looks amazing. It's just shattered.
That is proper mad.
something happens.
Watch
it takes
the
forever to
smiley
get to. Oh! That was awesome because you saw the actual shape of the CD and the cracks in it were perfectly like.
All right, so that's as much. The video's in the OneNote. You can watch it if you wish. I've just taken a screenshot. I'm gonna go out of potato mode now. Have a look. Have a look at the CD on your booklets, and you will notice that it's cracking from the outer edge. And we might be able to explain why that is in just a moment. So, let's just have a look. From the video, we are told that it was spinning, or it broke at about 23,000 RPM. Now, I'm going to ask that we estimate the radius to be 6 centimeters. We have then a velocity that we can determine. So let's figure out all the stuff. Firstly, we need frequency. So that's 23,000. We're going to convert minutes to seconds to get it in revolutions per second. But since the per unit of time is the denominator, we're going to divide. So it's actually spinning at around 383 revolutions per second, or 383 hertz, HZ. We'll do a side mission. We could find A centripetal first, but let's just go R equals 0.06 meters, V equals question mark, A centripetal equals question mark, and F centripetal equals question mark. So let's try and see what we can find. So V equals 2 pi RF, or 2 pi 0.06 by 383. This is solving for the velocity on the outer edge of the disk. So we're setting the radius to be the edge of the disk, and we get 144 meters per second, which is pretty damn fast. Okay, that's about, I don't know, 40% the speed of sound. Next, A centripetal is mv squared on R. No, it's not, it's just v squared on R, sorry. So we take that 144 squared, divide it by our 0.6, and we get a huge number. We get 3.46 times 10 to the 5 meters per second squared towards center of the CD. Okay? Towards center of circle, towards center of curvature, or towards the center of the CD. Now, we can't find the force because force is going to require mass. However, we can rearrange Newton's second law and say that I could give you force per unit mass. I could say that it's 3.46 by 10 to the 5 newtons per kilogram of mass. Okay? So just have a look. We've got rearranging acceleration. We can get units. That's another unit for acceleration. Joseph and Patrick, you stop talking now or you can leave. Louis, question.
For velocity, is it tangential to the...
Yes, so I got a little bit lazy. You should have written here tangential to the path of curvature. Just be careful. They can sometimes trick you in this topic and in gravity. They could ask for the force per unit mass, which is just a fancy way of saying F divided by m. It's a fancy way of saying acceleration. So we don't know what the force is, but for every kilogram of CD at that distance spinning at that rate, you would need 346,000 newtons. Even if we estimated, if I highlighted a section of disk and said that is equal to 0.1 gram, we could estimate mass equals 0.1 times 10 to the negative 3 kilograms. The force is still going to be quite large. It's going to be 1 times 10 to the negative 4 times our acceleration, and you're going to get about 34.6 newtons. And again, I'm forgetting direction there because I'm getting lazy. But again, on a tiny little speck, a 0.1 gram section of disc, in order for it to maintain that circular motion, the internal structure of the CD, the molecules of your plastic have to be pulling inwards at 34.6 newtons for every 0.1 of a gram. Okay, which is obviously it can't provide, and that's why it breaks. If we go back to an equation of, I'm just going to write it up here. F centripetal is m 4 pi squared r on t squared. In this case, t is constant. So it doesn't matter if I was to look at a section of disc near the spindle, or whatever it's called, or a section of disc at the edge, they are both travelling around in the same period. In which case, we can say that force is directly proportional to the distance that you are, because t is constant. In which case, it would be no surprise that it would break at the edge of the disc. Okay? I should have asked you first off, where do you think the disc would break? Some of you might have thought maybe it would break at the inside bit and it would fracture outwards. That, you know, it starts there and travels out, and others may have thought correctly that it breaks at the edge. I should have done that. Damn it. I'm thinking a lot of people might have picked incorrectly. Yes?
Is there a force opposing? Oh, yeah, obviously there'd be a force that when it breaks, it'd be greater than the centripetal.
Well, no, then after which, once it breaks, there is, well,
Yes.
other than gravity, it would travel in straight line motion, so it travels off with that initial speed, and then it might arc off air resistance and gravity.
Yeah. What force would cause the breakage?
Well, it's not the force that causes the breakage, it's the lack of force.
Lack of.
Basically, the edge of the disc might say, I can provide 3.45 newtons for every kilogram. That's just maybe the tensile strength of the CD, the plastic. And we're asking it to provide 3.56. It goes, no, sorry. All of a sudden, it can't.
When the centripetal.
It literally accelerates out from the centre. And if you're accelerating away from the centre, you're now travelling in a straight line instead of a circular. Yes, J-Bon.
We ever get sort of a hybrid bastard question if it's like a thing like that. A disc like this, say for example, shatters, and then we have to work out the velocity of that.
Yeah. Yes.
Based on
But again, remember the first example from yesterday's lesson. You've got to ask yourself, are the points travelling at the same speed or different? Or are they travelling at the same time or different? Depending on the answer, it's either going to be the inverse proportion or the direct proportion. Here's a lovely little example. I've got a ball bearing here, and I can roll it around. Ooh, I can roll it around. In fact, this isn't... Oh, I spoiled the fun. Here's an unbroken plate, and I can spin... Oh, gosh darn it. I can spin the ball around, and obviously what's producing the inwards force is the reaction force on the wall. The normal force is pushing the ball in a circular path. It has to, or else the ball bearing is just going to push through it like some crazy X-Man juggernaut. Yes. But here is a hole in the thing. So, if the wall can no longer provide a normal force, and I get it spinning, which way shall I spin it? This way. It travels off in a straight line. Look at that. This is the greatest demo. All you need to do, put a hole in a solid thing, get it spinning around it goes, boom, and then it travels off in straight line motion. Okay? And that's what the piece of the CD would be doing. Now, I foolishly forgot to give you a spare page titled Turntable Demo. Could you please find yourself a spare page? Apologies, but you'll need to find some paper. Okay. You don't need to draw this. But essentially, we've got a brass mass that we're going to get travelling around on a turntable. Okay? So, here is my turntable, and it spins. It can spin at 33 RPM, which is about once every 2 seconds. In fact, it's got a period of 0.55 seconds. I can spin it up to 45 RPM. Some discs require different speeds in which for them to work. Obviously, the turntable's there, and I've just got a piece of wood I've got a scale every 5 centimeters marked from the center, okay? But before we jump into stuff, I've got to find the center again, there he is. Remember I said, centripetal force is not a real force. In this case, friction is going to push this brass mass towards the center. If there was no friction, it would go sliding off, okay? So at the moment, its speed and its radius is saying and its mass is saying I need a certain amount of force, and friction is saying, yep, I gotcha, I can do that, okay? However, at some point, try again. At some point, friction's still got him. He's saying, I've just increased I need more force because I've increased my distance, and friction's going, yep, I gotcha. Eventually, we'll reach a limit where the required centripetal cannot be provided by friction. I'm going to now do that. Ready? Here we go. Friction couldn't provide the centripetal force. We exceeded a limit. Boys, whenever you guys are cold enough, you can turn off the air conditioner, okay? Because that was freezing. I was just in front of it. We're going to do a little quick bit of figuring out what the coefficient and what the friction is on this level surface. So, I've already done the sums, but let's just quickly sketch. We're going to go back to year 11 level and consider the forces on an incline. Here we have the normal is mg cos theta. Here is our weight force mg, and then we have a backwards force of friction, okay? Now what we require is friction has an equation. It's mu naught n. So it's going to be mu naught mg cos theta. And we know that the force due to gravity is equal to mg sine theta. Okay, where can I'll just draw the edge of my page just so I don't run off the edge of the page. Now what we need, at some point, the force of gravity needs to be greater than or equal to the force of friction, after which it's going to slide down the incline. Okay, if we plug everything in, mg sine theta, mu, it's actually mu s for static, but it's not really in the course, mg cos theta. Cancel-y. The mass does not determine what friction is. Cancel-y. Gravity does not determine what friction is. What we get is the angle. What we get is that mu s is, take that across, sine theta upon cos theta tan theta. All I need do is measure the angle at which this guy starts to slip. Once I have the angle, I can figure out the coefficient. Now you'll just need to trust me that in a previous year, I placed this on the surface and I slowly raised up the incline until it started to slide. I measured the hypotenuse and I measured the height vertical. I was able to determine that the angle of slippage is 15.8 degrees. Basically, we're just skipping about 2 minutes of tedious busy work. Theta equals 15.8. Therefore, our coefficient is the arctan of that. It's 0.283. So basically, now we know that on a level surface, I simply need to push laterally with more than 0.283 of its weight force. Whatever its weight force is, if I apply 28.3% more, I'll be able to get it sliding. Okay? So that was a little side mission. So now we're going to play with the turntable at various settings. Okay? You guys are okay with the air conditioner? You can turn it off if you want. Okay. Before we go, let's just figure out F max provided by friction is going to be mu mg 0.283 times 0.05. It's a 50 gram brass mass. And so our maximum force is 0.139 newtons. That is obviously on a flat incline where cosine of 0 equals 1. Okay? Just bring this down. Okay, we are going to consider two various speeds. We're going to figure out first a frequency of 33 RPM. So again, if we divide that by 60, we get a frequency of 0.550 hertz. A time period is the inverse of that, which gives 1.82 seconds. Okay? What I'm going to do is put this mass at the edge. Now, it's at 44 across, it's 22 centimeters to the edge. I'm going to set the radius of my circular path equal to 22 centimeters. And we're going to basically figure out what's the required force that friction has to push inwards so that this little brass mass can maintain a circular path. This is how I want you to set up every question from this point forward. You say that the sum of all forces is that of friction, which produces F centripetal, which we have an equation that's mv squared on R. Or, breaking that wall, it's m 4 pi squared r on t squared. Just being lazy. So please, make all of these statements. You're basically saying that you understand that centripetal force is not a real force. You're saying that this mass is accelerating, that it's a combination of various forces. In fact, if I asked you nicely to determine all of the forces, you've got the normal force, you've got the weight force, and you've got friction. Those are the three forces acting. Well, we don't care about the verticals because it's not accelerating up or down. So really, the unbalanced force is solely in the horizontal. Okay? So, we get, for a 50-gram mass, travelling in a circle at a distance of 22 centimetres in a time of 1.82 seconds, the required force is 0.134 newtons towards centre of circle. Okay? Which you should notice from above is less than the maximum friction. So if I crank this, spin this deck, we're good. It's able to travel around. It's able to travel around. It's close to, isn't it? The required friction was close. I'm going to just put it on a sticky spot. It is very close to 0.139. So maybe when I took the measurement, I might have gotten a slightly heterogeneous surface, that one area is a little bit stickier than the other. I was assuming that the surface was homogeneous. Okay. All right. Now, let us consider the next revolution. Let's spin this bad boy up a bit faster. Let's go to 44 RPM. 45 RPM. So again, converting our minutes to seconds gives us 0.750. Time is the inverse of that frequency, so we get a time of 1 over 0.75, which is 1.33 seconds. Now, here's what I'm going to do. The question is, what's the maximum distance I could place this such that F max is equal to FF, which we said was F centripetal, which we said was this guy up here, 0.139. So we're going to set our centripetal to 0.139, and we're going to ask, where must I place... Oh no, I went off the page. That's bad. Oh well. So, we are going to spit out our equation again. Sum of all forces is that of friction, which produces centripetal, which we know to be mv squared on r. But I'm not going to do v... R, V. Well, we can't solve this without using our little m4 pi squared r on t squared. And I'm going to rearrange for r. So, I would say that r equals F maximum times t squared, and then I'm going to divide by those coefficients of m4 pi squared, and that should give us I'm just in my little friend dimensional analysis here. You could throw everything in, you would get units of meters. Wouldn't that be a fun little side mission? 0. What was that? Thought I heard something. 0.13. What was it? 139?
125.
Calm down, you eager beavers. Jeez. God. Out now, before we shout out the number, let's consider that at 22, when I spun it up to 45, it slipped off at 22. So obviously we'd have to bring it back. I'm expecting a number less than 22. We've increased V, so we'd have to decrease R from mv squared on R. So we get 0.125 meters or 12.5 centimeters. So yes, you are correct in assuming, if I set this now, I'll place this, the center of this brass mass, I'll put it at about 14, okay? Just so we make sure that it spins off. Here we go. Oh my gosh. Off it spins, okay? And then if I placed it, let's say at about 10, hopefully, fingers crossed, it should stay. Because at 10, the friction force is, well, it's less than the maximum of 1.39. The required centripetal force is less than the maximum friction can provide. Fun stuff. Okay? Alrighty. Now, that's as far as I wish to go. Oh, hang on. No. I'm going to give you some time now to work on some Jancoli physics. But before we do so, remember I showed you a couple of different questions where we had two objects travelling in the same time, and so V was different. Yeah? And we looked at the proportionalities. And then we had two cars travelling at different speeds, so the time was different, and the proportionalities were then different. Have a look at this question from 2014. Two balls on a string, M1, M2, at radiuses R1, R2, write appropriate expressions for velocity and tension in terms of those variables. This was the 2014 WACE exam. Now, I want you to look at Jancoli physics on the screen, circular motion, question 23, a level 3 doozy. Have a look-see. Right. Now, deriving an expression for tension, that was part C of that 2014 WACE exam. Something is telling me, I think whoever made the 2014 WACE exam went looking for inspiration for types of questions, and they opened up Jancoli's 6th edition, and they saw this question. They removed the frictionless table because in the question it says, ignore any effects of gravity and air resistance. So imagine that someone's spinning this two-ball string thing in the middle of space, away from any gravitational fields. But here it just says, ignore friction, in which case the only force acting is the tension along the string. So, I'm hoping that if you can have a look at enough of the Jancoli questions, whoever's making this year's WACE exam, when they go looking for inspiration, they might turn to the same book. Okay? Now, the great thing about Jancoli is there's always going to be heaps of different scenarios and different contexts and different ways of asking you about these equations. Unfortunately, gentlemen, this chapter 5, that's titled Circular Motion Gravitation, it covers like the next 3 weeks or 4 weeks of this course. So, I just want you to look at the yellow highlighted. Alright? Once we then get to vertical circular and conical circular and gravity, I will highlight different questions in different colours. So please do not even bother looking at any other questions. At this point, only look at the yellow Jancoli. Okay? So guys, you've got the next 20 minutes. I want you to play with these questions. Question 1 is dog awful easy. Question 3, this was the question in WACE that lots of students struggled with. And in all the different revision seminars that I've run since, kids are always asking me, how do you do that question? So, you know, have a go at the level 1, have a go at the level 2. If you're finding them easy, jump straight to that level 3 question. Mr. Murray signing out.